So hello everybody. I have to say there's a lot of people coming here. It looks like Ryan here is very controversial. It's a pleasure to have him here. He's actually the author of Node.js. Just out of curiosity, how many of you guys have heard about it? Yes, the first time I heard about Node.js, I said, what a crazy guy. Why would he try to put JavaScript on a server when everybody's trying to put Java on the client? But you know, since then I have seen the light, and it's quite interesting and amazing stuff. So I'm very excited to have him here. So Ryan's going to talk about his project, Node.js, and I'm going to let Ryan do the work.
Thanks, Mishko. Hi. Yeah. Well, just get started. Right. So Node is this project to bring JavaScript to the server side, but in particular, I'm very interested in scripting network servers, which gives the project a certain flavor. I think that scripting servers is a good road into scripting other things, like GUI applications. If you can do well with a web server with 10,000 people connected to it at a time, then you can probably handle GUI applications. So I'm very focused on how to deal with TCP connections and UDP things and that sort of thing. So I think the basic thesis here is probably that we need to avoid making abstractions. There's a lot of different ways to write servers, especially for high-level languages. And everybody kind of employs their own flavor of how to abstract this problem of dealing with possibly thousands of different people connecting to your server at a time. And I think that we need to be careful about how we make these abstractions. And I mean, the problem is that at some point you might have to use those, and you just might feel trapped by them at some point. So really, I think one of the major points of Node, which I'll try to describe to you, is just to avoid making all these abstractions and just kind of present the low-level interface and allow people to build on top of that. So we want to write high-performance servers easily. Important point is easily. I think writing high-performance servers is kind of a solved problem. What we want to do is be able to throw them together in a matter of minutes instead of months. So without going into too much detail, I think it's well known that using an OS thread for each TCP connection to your server is not optimal. These threads are too heavyweight to be handling many thousands at a time. The context switching and the memory overhead is just too much. That's why you have projects like Nginx and Light HTTP and Cherokee that have a event loop, that are event loop web servers versus Apache that use threads. So in order to get beyond this limitation, you somehow need to multiplex a lot of I/O into each OS thread. This is how you achieve these really high-performance servers. And it's really not a mystery how this is done. You use some I/O multiplexer, like ePOL or KQ. You do non-blocking I/O calls. You don't share memory too much between your TCP connections. And then you spawn a bunch of threads. And you probably do some sort of pre-forking sort of thing so that you can accept connections on each of these threads. So each thread has an event loop running. And you push many thousands of connections into each OS thread. So this is basically how super high-performance servers are structured. at least in C, that's how they're structured. In higher level languages like Python or Ruby or Erlang, there's different abstractions that people use on top of this sort of event loop plus thread model. And I think there are basically two ideas. One is that you can have green threads, which is kind of a fake little thread that presents your I/O as blocking so that you can go query database, return some value, read from socket, returns data from that socket. And it looks very blocking, but underneath you have multiple execution stacks, and you jump back to the event loop. And you're all contained inside of this big OS thread and jumping between these little green threads. Underneath, it's the same thing, though. Green threads are great. You can make your code look very synchronous. You can achieve very high performance concurrency. But at the end of the day, it's an abstraction on top of an event loop. Erlang processes are a bit more interesting. Basically the same thing. They're processes. They're not actually processes. They're green processes, if you will. The difference is that they don't share an address space with the other processes. They're isolated somehow. And because of this, the Erlang scheduler can open a bunch of different OS threads and schedule these processes into each of these threads as necessary. So this is super cool because you can now scale over multiple cores kind of transparently. And I think what's really cool is, and kind of the killer feature of Erlang, is that you can kill these individual processes without disrupting the rest of the system, just because they're in their own address space. And then there's some other concepts of how you deal with really high concurrency. And I think a lot of these concepts can be summed up in message passing systems, like actors. Some little entity that passes messages between different things. The idea being that if you don't share memory, you can scale across multiple kernel schedulable units. You can scale across multiple OS threads over multiple machines if you pass messages and tell each other what to do. So these are great, but this is kind of at a higher level than we really want to talk about. We're talking about kind of what the concurrency mechanism looks like to the programmer. What does it look like at the thread level? This is something that's built on top of these other mechanisms. So all these things are great. Lots of PhDs have been done with these ideas. And these green threads and Erlang processes are super cheap. You can spin up thousands, tens of thousands at a time, and cost almost nothing. But underneath, it's still an event loop with some OS threads and some non-blocking I/O. So I like C, and I actually like programming with non-blocking I/O and event loops. I don't find that this is a bad thing that we need to avoid necessarily. And in particular, I like this concept because when you get notified that a file descriptor is readable, and then you read some data from it, then you execute some callback. And when you're in that callback, you're kind of in a world unto yourself. You're somehow side effect free. I mean, not totally, because you can call printf and that might do something funky, or there is definitely still some I/O, some side effects involved. But largely, you're just with yourself. You can run your parser. You're not going to be unscheduled. It's just somehow how simpler than dealing with the fact that another thread might start running at any point, and that you need to make all of your functions totally thread safe. It's easy to reason with. And I think the other point about just this kind of basic C event loop non-blocking I/O model is that basically the first 10,000, 20,000, 30,000 TCP connections or Unix sockets or whatever are free. I mean, they can be put into a single OS thread. You don't need to really worry about multiple core concurrency when you're only dealing with 10,000 connections at once. Now, if you're dealing with 100,000 connections at once, then things have to change. But at this level of, say, less than 10,000 or less than 20,000, I think it's fairly appropriate to write a single-threaded system. And I think there's a lot of applications where you don't need to worry about more than 10,000 I/O streams at once. In particular, GUI applications or simple request-response web servers that aren't holding connections. You don't have 10,000 people connected at a time, like a long pole server or something. But you're just sending some request-response cycle. You don't have so many connected at a single time. Or maybe like implementing a fuse file system. You really don't need hundreds of thousands of file descriptors. And this just simplifies everything. If you can just stay inside of one thread, you can have global variables. You don't need to worry about locking. You don't need to do any IPC. Your world is very simple and sane and nice. There's problems with this. Well, first problem, which is not listed, is that you have to program in C, which is painful. And you can't think synchronously. No, you have to, yeah, right. You can't think synchronously. Everything has to be somehow non-blocking, right? You can't just read data from a socket and expect that data to arrive. You need to wait until the data comes to the socket and then be notified when that's ready. You can't just make a database call and expect the results right away. You make the database call, you go away, you come back. It arrives later on. And it's kind of all or nothing. You can't really mix in non-blocking libraries, which is a really difficult thing, especially if you're interfacing with something like MySQL that doesn't have a real non-blocking client library available readily. So if you're writing something that needs to interface with MySQL, you probably aren't willing to rewrite libMySQL client. So this approach is not appropriate for you. OK, so back to our goal. We want to write high-performance servers easily. So basically, I'm pretty much OK with C and event loop and non-blocking I/O. But C is kind of the annoying part, right? It takes a very long time to program in C relative to some of these scripting languages available. So enter JavaScript. In the last year or 2 years or so, it's become clear that there's an arms race among companies like you guys and other guys for making these JavaScript virtual machines very fast, which is great. V8 is released BSD licensed. Thank you. So it's an appropriate language in terms of performance to use. More importantly, JavaScript doesn't come with any preconceived notions about how to do I/O. It has no printf method, right? It's only has the DOM. That was its only I/O before. And that's great, because it probably would have been totally messed up if somebody else tried to do it. it's great because we can experiment and we can try out all these different ideas about how I/O has to do and not have to play into how JavaScript already does I/O. Browser JavaScript, importantly, is a single threaded interface. It has non-blocking I/O. You make XML HTTP requests, and well, I guess you can do it synchronously, but for the most part, people are doing all this stuff asynchronously and getting callbacks. When you click a button, you get a callback. You don't start a thread for each button on your web page. And this has worked out brilliantly. What a great idea. It's very easy to program with. And personally, I think that this is the reason that the web browser and JavaScript have become as popular as they have. It's a very simple interface. And I think the last point is that we have a generation of programmers who have grown up now learning how to interact with the computer through this sort of evented browser interface. And so they're very familiar with what it's like to program with callbacks. That's not necessarily true of Java server-side guys. They find callbacks and stuff very difficult to deal with. So Node is a project to make a set of bindings to V8 to do non-browser work, to access sockets and files and, well, other things. What else is there? I guess that's it. Doing timeouts. So it only exposes a non-blocking asynchronous interface. It's only one thread, and it's only one call stack. There's no green threads inside. There's no coroutines. It has a lot of low-level features, like half-closed TCP connections that nobody cares about until you really care about it, or TCP throttling, or UDP, and has really good HTTP support, which is important because HTTP is the backbone of our society, basically, these days. So I said that we should be careful of making abstractions. I think that Node is attempting to not make any abstractions. What it does is take away certain interfaces. Well, obviously, it turns these POSIX APIs into JavaScript interfaces. So, I mean, at some level, that's changing things. But more or less, it's limiting you away from things that you shouldn't do, like synchronous I/O, rather than exposing new high-level ways of doing things. So because the interface is purely non-blocking, users tend to achieve decent concurrency without knowing what they're doing. You don't have to know what an event loop is or what non-blocking I/O is. You live in this non-blocking jail when you use Node, and it's impossible to escape. So you start writing a web server and you run Apache Bench on it, or you start having a bunch of people from Hacker News connect to it, and you go, wow, hey, it works pretty well, and everybody's very surprised. It's only that it's not that Node's necessarily so fast compared to, say, other evented web servers. It's just that it doesn't let you do anything that you shouldn't be doing. And because it's this non-blocking jail, there's no mutex locks. Only one callback is happening at a time. It's like browser JavaScript. There's no thread safety issues. Only one thing happens at a time. So once an event is emitted, once your socket says that it's readable, you're basically side effect free, almost. There's some exceptions. But that's what you want. It calms you as a developer. you can relax and just kind of chill out because you just don't have to worry. There's not going to be some other thread that jumps in and starts executing a bunch of stuff. When you get your event, you've got it. You've got control of the process. And I think that at least for beginners, at least for not super advanced Unix programmers, this is a fairly nice interface to have, to not have to worry about these things. So the major complaint is that Node is single-threaded. Oh my God. That means it can't scale across multiple CPUs. It doesn't automatically scale across your data center. This is total crap, right? I mean, don't you know, Ryan, that like we have computers now with like 5 million CPUs and like we've got really big data centers, and any new programming language should definitely be able to just scale across the entire world. Well, don't fear. You really should not fear. There's this great thing in Unix called processes. And when you have multiple processes, the kernel can schedule them however it wants to. And so this is really not a cop-out. I really think that this is how you should scale to multiple cores or to multiple machines. You simply use multiple processes. Depending on the problem, different problems require different solutions. You might attack this in different ways. If you're a web server, you might want to load balance. Say you have 8 cores. You might want to spawn 8 node processes, start a server file descriptor, and just send message that file descriptor to the other processes. Node provides this primitive. It's an age-old Unix trick. And then each of these processes can simply accept connections into their own world. This is a fine way to scale. This is how Nginx does it, right? It's a pre-forking web server without the forking part, which you can ask me about later. Or just traditional IPC. We make creating Unix sockets very easy. So there's no excuse to not pass messages around. You can just open /temp node/temp/node.sock or whatever and have all your processes connect to it and start sending it JSON messages over this and tell it what to do. This is how you scale to multiple cores. This is how you scale to multiple machines. You replace Unix sockets with TCP connections. So Node doesn't have a built-in actor library. It doesn't have some sort of framing protocol for doing IPC nicely. It doesn't have an RPC system. But it could. It's fairly trivial to write any of those things on top of it. So if you want that, you can check out, for example, Peter Grice's web worker module, which does exactly that. And yeah, memory, these are processes, so they are isolated. You can kill them individually. If you have a server, if you actually had your 8-core server and you split your server socket across all the 8 cores and you're accepting connections on all of them, that's cool. If something goes wrong, you might bring down one of those processes. Like in Erlang, remember, we could bring down any connection, basically, individually, because each thread, each process was in its own address space, and you could kill them individually. They could crash by themselves. That's fine. That's very cool, actually. You can do the same in Node. You'll just bring down 10,000 connections with it. But not necessarily the other 7 processes that you have running on your server. So you could imagine a system that resends that server file descriptor after a crashed process back to it. Node is very low level. It doesn't address these issues. But these issues can be built on top of it because we're trying to do the correct building blocks that you can do the rest in JavaScript on top of this. So just quickly about the architecture of Node. Node is basically three things. It's V8 to interpret JavaScript. It's a thread pool to do file I/O or any other blocking system call. You can't get around that. So it has this internal thread pool by itself, but it's only for executing these blocking system calls. And then it has an event loop library, which is fairly simple. It's instead of having to write a backend for KQ and epoll and event ports and select, this is a very small layer on top of it, libev, that allows you to simply compile to those things depending on your platform. So it eases development very, very well, very much. And then it has some sort of thin set of bindings in C++ that more or less expose some very low-level interface, basically non-blocking POSIX calls. The rest of Node is written in JavaScript on top of that. And so the APIs that you see on the documentation are mostly implemented in JavaScript on top of these rather low-level C bindings. So that's the architecture. I think it's fairly simple. So let me just do some examples to talk about to show what I'm talking about here. So first of all, just to make it totally clear, Node is a command line tool. So you have to download it and compile it. It doesn't have very many dependencies other than Python. V8's included. So here's the first example. This should seem very familiar to browser JavaScript people. You can do a set timeout, which executes its first argument, a callback, after n milliseconds, which is its second argument. Exactly the same as you have in the web browser. And we also have this console log thing, which is like the Firebug interface. That prints something to standard out. So what this program does is it prints hello, and then it prints world after 2 seconds. Hello first. So importantly, Node is exiting after it's done. So it prints hello, it waits, it doesn't exit, then it prints world and it exits. So Node always exits after there is no other callbacks to be completed. When the event loop has no timeouts or file descriptors on it, it exits automatically. So if you wanted to do this, just to make things super explicit, put that text into a hello world.js file, call it with the Node program, you get hello. 2 seconds later, you get world, and it exits. So another example, what we could do is loop and print hello every 500 milliseconds. And then on sigint, on the interrupt signal, when you hit Control-C, you can print bye, and then exit the process. And so what we're going to do is use the special process object. So in browser JavaScript, you have this special window global variable. In Node, you have this process global variable. It's kind of, Node is very process oriented. You are inside a single process. Very much like in browser JavaScript, you're inside a window. OK, so first 3 lines. You're printing hello every half a second with the set interval function, which is just like browser JavaScript. And on line 5 through 8, you are setting up a callback. You are listening for the sigint event on the process object. So the process emits the process object emits a sigint event when it catches a sigint signal. Then it prints bye. And because we've overridden the signal handler, we have to exit the process ourselves. So we do process exit. Right, so the process object emits an event when it receives a signal. So this should all seem very DOM-like to you. When you click a button, you get a click event. When you mouse over something, you get a mouse over event. When you get a signal, you get a SIGINT event or whatever. So this should seem familiar to browser programmers. So just a little bit about this process object. There's a lot of things that hang off of it. So you could get the PID and the arguments and the environment, and could get the memory usage, which is kind of cool because that's totally platform dependent, and spent a lot of time researching how to figure out the resident memory for every platform, and so on. So the process isn't the only thing that emits events in Node. Lots of things emit events. A TCP server emits a connection event every time somebody connects. An HTTP upload, if you're uploading a movie to a web server, emits a data event every time a new packet of information comes. This event emitting is the kind of the fundamental model in Node. They're kind of nice interfaces wrapped around file descriptor notifications. So let's do a little TCP server. You listen on port 80. When somebody connects, you send it a message. You send it hello, and then you close the connection just to see what servers look like. So this requires a module. Require is how you load a module in Node. This is the common JS module specification. So you load the net module, which is how you create a TCP server, and you do net.create server, gives you a server instance, and then you listen for the connection event on that object. That connection event gives you a callback with a socket, which we call C here. And all you do is on that callback, you do a C.end, which sends the argument to the connection and closes it in one fell swoop. And then if that's all you had, if you omitted line 9, the program would just exit immediately. But if you start listening on port 8000, which is what line 9 does, then the process stays open because it's waiting for connections now. So if you wanted to try that, you could put it into server.js and run it with the Node program. And then you could telnet to port 8000. And you would get hello, and it would close your connection. So you can do file I/O in Node as well. This example uses the FS module, which is where all the file system methods lie. And what we do in line 1 is just pull out the stat function from that module. And what we want to do is find out the last time that EDC password was modified. And so we stat EDC password, just like the POSIX call, and we get a callback. So, right, I mean, very likely EDC password is somehow cached. And this function, this system call that we actually make to stat, executes very, very quickly. But it could be that it's not. We don't really know. And it could be that an actual physical disk has to spin to figure out the time that EDC password was last modified. Because of that, we don't want to wait for that, especially if we're inside of a crazy server that's got 10,000 people connecting to it at the same time, and we have to manage all these people at the same time. We can't wait for some disk to spin very, very slowly. So we don't. We do it in the thread pool, and we get a callback when the internal thread pool has executed the stat system call. So that callback gives you 2 arguments. The first is error, which is some sort of error object. If this call was successful, then that object is null. If not, it's some error object saying EDC password was not found or something like that. So if we have that error object, then we could throw it and we'll get a stack trace. Otherwise, we're just going to print out the M time from the result. Okay, so a simple HTTP server, getting progressively more interesting. So we can load the HTTP module, and we can create an HTTP server on line 3. And what we get is a callback. This callback is not executed for every connection, but for every request, because of course we have keep alive sessions these days, and we can have many requests per connection. And for each request, you get a request and response object. And all we do here is we write a header, which says 200 OK, content type text plain. And then we write hello, and then we write world, and then we end the response. And then on line 9, we bind to some port and start listening. So this is slightly more complicated than, say, if you're familiar with Ruby, the rack interface, where you just return the body of the response. But there's a good reason for this added complexity. And that's to enable all the many possibilities of things that we can do with HTTP requests and responses. Example forthcoming. So to try this out, put this code into httpserver.js, run it with the node program, curl it, and you will get hello world with some headers. If you notice, happily the connection defaults to keep alive. Yes. And also transfer encoding is chunked. It's not the identity transfer encoding. There's no content length. That's because while we were writing out the header, we didn't really know how long the body was. Somebody could have just kept streaming some responses, some more data. So we couldn't possibly have given a content length. So the server defaults to chunked encoding and chunks those things out so that you can stream them. OK, so now a real streaming HTTP server. Everything's the same here. We write 200 OK, content type text plain. On line 5, we write hello. But now on line 7, we set up a timeout for 2 seconds. And at the end of 2 seconds, we write out world and end the response. So this timeout, it's not a sleep. The server does not shut down when it hits the timeout. It simply goes back to the event loop. It registers that callback and goes back to the event loop. It hangs that connection. More people can connect to it, and they also won't get responses immediately. It can handle many connections at the same time. It's not sleeping. The process doesn't shut down. It's simply waiting for those timeouts to happen. And when those 2 seconds are up, it responds with world, 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 world to all the various requests that are connected to the web server. This may seem initially slightly esoteric, but it's exactly what you need to do the sort of long polling type of websites that are becoming more prevalent these days. You need to be able to hang a connection and respond to it when you want to respond to it, not when the server wants to respond to it. And we can do that with Node. It's very good at that. So if we wanted to try this out, we could put that code into httpserver2.js, run it with the Node program, curl it, and we would get hello. And 2 seconds later, we would get world. We can stream responses. So this HTTP module is quite low level, if you noticed. It allows streaming requests and responses, allows requests to be hung while waiting for other things, which is necessary for long polling, all of what I just said. The HTTP interface is at the message level. It doesn't try to understand the content. It only tries to pull out the body and the headers of the HTTP message. This is a good level to work at because HTTP in general is extremely complicated, and there's very many things that you can do with it. But by presenting this level of abstraction for HTTP just on the message level, you can basically do what you want with it. You can layer on whatever sort of framework or ignore what you want to on top of that. All we try to do at the node layer is parse out the HTTP messages, which is non-trivial, very non-trivial. HTTP is very difficult. And you might be like, what? No, it's not. I mean, it's just like HTTP slash 1.1 space 200 OK, return, content. You know, you think it's very simple, but it's very not simple when you get into HTTP 1.1 with keep alive sessions and chunked encodings and all the various bugs in different web servers and web clients. There's a lot of intricacies in there. And so this is made possible by an HTTP parser, which parses both requests and responses. The interesting thing is that it doesn't buffer anything. It never buffers any header. It never buffers any body of the message. It just walks through the message and parses it as it comes in. It's interruptible. And it requires only 36 bytes per HTTP stream. That's per connection, which I think is optimal. I mean, if you have many, many people connecting to a web server at once, I mean, you have to be very careful with the memory usage per connection. You can't allocate 4 megabytes of memory for every connection to a web server if you want to handle 10,000 connections. Well, maybe you can, but it becomes heavy. It's much better to try to be very careful with the memory you use per connection. Right, so we can just 2 more examples. We can execute child processes. So this uses the child process module. It pulls out the execute function. And here we execute ls/, right? Which again may spin the disk. We have no idea how long this process is going to take to complete. It may take forever. We have no idea. So we have to have a callback here. We simply cannot shut down our server and wait for ls/ to complete. We have to set up a file descriptor, a pipe to that sub-process, and stick it on the event loop and go back to the event loop and wait for it to complete. So what this function does is it buffers up all the output from standard out and standard error and returns it to the callback. Again, it has this error function like in the file module. So all this does is prints out ls/, opens a ls/ sub-process, takes the standard out from it and pipes it to the own standard out of node. So, but we don't really want that all the time. Like we don't always want to force buffering. So there's a lower level API to start child processes. Where we can totally do streaming through the standard error, standard out, standard in of the child process. They're just pipes, so we can just talk to it. So this gives you a very simple form of inter-process communication. So this is called the spawn function, which is how execute is implemented. And here we're going to just spawn the cat function. The cat program. And so cat, which you all know, when you write to it, it sends whatever you wrote back to it. It echoes everything. So we write on line 5 to cat's standard in, hello. And we set a timeout on line 7 through 9 to write bye to cat. And then close the standard in of cat as we write that. And cat has the property that the child that it will exit when its standard in is closed, when you control D, right? And then what we're going to do is we're just going to listen on cat's standard out, and we'll get data as it comes out of cat, and then we'll just pipe it right into our own standard out. And so what we'll see is we'll see hello, 2 seconds, bye. This is cool. This is a nice tool. Maybe you want to tail-f a log file or something. You can just keep streaming this data in. So connecting streams is a fairly common sort of thing that you want to do. You take data from here and you put it out there. And so for this, we have kind of a nice little function for this called sys.pump. And so this is the exact same example with the cat, except on the last line, instead of actually setting up a callback for the data event on cat standard out, we just do pump cat.standardout to process.standardout. So it's just going to pump the data from that stream into our standard out. It's the same thing, just sets up a callback internally, but eases the coding. So I said we should be fearful of abstractions, and I'm also fearful of this abstraction. But we're playing around with it, and I kind of like it. And I think that we're going to have more things like this. Because, I mean, basically, most of our computers are proxies in some way, right? You connect to a database, you start getting some data, you kind of like stick on some HTML tags, and you send it out the other side, right? I mean, more or less, this is what our processes are doing. They're just kind of piping data from one place to the other and, running some function across it. So I would like to have more sort of pump-like functions. This one's fairly simple. It just pumps it directly. But maybe we can have other things that add stuff, some sort of mapping pump for streams. OK, so very quickly, some fun modules for Node. Right? You can create add-ons for Node, and you can create your own modules. So Tim Caswell's step library allows you to do some async control flow. So you might think that doing all of this file I/O with callbacks is going to get extremely tedious very quickly, right? You're just going to go in indentation levels very quickly when you have a bunch of serial things to do. Rather than immediately jumping on the green threading bandwagon, let's just chill out a while, a year or two, and think about how we could possibly do this in other ways without going through the process of adding multiple call stacks and writing our own little scheduler. So what does this thing do? It allows you to set up a bunch of functions that can be called in serial, in parallel, and makes it rather easy so that you don't have to go in. It queues them up. So Matt Ranney's PCAP library. PCAP is a very asynchronous sort of thing. It's a binding to libpcap, so you can pull raw packet data off of an interface, which is fun. And you could imagine many uses for throwing together a little node server that can sit there idly and just kind of listen to packets coming in. There's an MDNS module, so for service discovery sort of things. And this is another one of these very asynchronous sort of things, waiting for some web server or some message queue out in your data center to, to notify and advertise itself that it exists. So you can just get a callback, and your process just sits idly and waits for that. There's no overhead. Oh wait, ignore that. So that's it. I would like to take some questions. I think I have 7 minutes or so. Yeah.
Is module loading also asynchronous? So like the require call?
So the question is module loading also asynchronous? There is a way of doing asynchronous module loading. And initially I was, remember when I said almost all the time when we had these side effects? This is one of these. So initially when I wrote Node, it was all asynchronous, and you had to have a load callback, much like in the web browser where you get a load callback when all of your scripts are loaded. I've backed off of this quite heavily in the last half year, and now most requires are synchronous, and all the libraries are using synchronous requires. I think this is an okay compromise. It pained me for months to drop the purity of having an asynchronous module system, but I think it's okay. There is a way of doing asynchronous module loading, but I think it will be removed in the near future just to clean up the code a bit. I don't encourage it. Yes?
So just a follow-up question. Would you be able to say a couple of things about what pain points were causing you to switch to synchronous modules?
So the question is, what pain points caused me to switch to module loading? Well, to synchronous module loading. The pain point is a mailing list called CommonJS, which is very annoying sometimes and demanded that modules be in a certain way. And I felt it necessary to comply with them. In retrospect, I don't find it such a bad idea. You are, of course, accessing the disk, which may be over an NFS sort of thing, but these are not the sort of web page sort of things that are being loaded, you know, a million times a second, that you really need to be careful about how fast it loads. Disks are pretty fast. So it simplifies the code a lot to be able to just stick in require, and not have to do a onload callback. And I think that's been a relatively okay compromise.
Well, you described at the beginning of your talk a series of reasons why asynchronous loading, asynchronous callback style helps you along. You've discovered at least one case where a synchronous callback style is either beneficial or easier for some subset of the population. Do you think that there's some more generalized template or more generalized style of programming that you need to extract away so that both of these groups can be satisfied?
Okay, so I'm going to repeat your question, even though it's very long. Yes, there are situations where synchronous I/O is very beneficial, like module loading. And you're asking if maybe there needs to be some sort of abstraction that makes use of this fact of life, that sometimes you want to do things synchronously. Maybe. I'm not so sure. There is so the other thing that I have in here is I showed you some file system methods that were asynchronous with callbacks. All of those have synchronous counterparts. Basically because I don't want to be, you know, a total asshole and force everybody to do these sort of asynchronous things. There's really two parts to your program. There's the loading and starting up phase where you're going to like move this thing over there and you're going to delete that and you're going to create the socket and do all of these sort of things. And you don't really care how fast that runs. You're going to load modules and stuff. The setup phase of your daemon generally is synchronous. It's when you get into your event loop for serving requests that you want to be very careful about this. I don't know. I mean, somebody needs to write a PhD thesis on this. Like I said, I just want to bind to these kind of simple things that we know about. And I will give people synchronous file I/O. If they do it in servers, yeah, it will probably suck a little bit, but it won't be terrible, right? The important thing is to never let them do synchronous network I/O. Yes?
If you look too much at remote providers that are required.
Maybe, can you come up to that microphone? I'm not sure if it works.
Have you looked at remote providers for require?
Sorry?
Loading modules not off the local disk, right? Any kind of plugin system for require where you could pull it from somewhere else. Right.
So we have all this HTTP stuff built in, so we can pull modules off of HTTP. I will also probably remove this because it must be asynchronous because the HTTP has no synchronous counterpart. But also, I just don't think it's necessarily a good idea, and it's too annoying. And I just want to be pragmatic about this. So module loading very likely will only be from the disk. I'm backing off of network loading. Of course, you yourself can, get some URL and evaluate it yourself. And there's fairly good evaling, sort of creating contexts and that sort of stuff, bindings in Node that are exposed to users, so that you can actually do your asynchronous loading yourself. But I don't think that it will be part of the suggested thing. Yes?
How do you deal with invoking the DNS resolver asynchronously?
So how do I do asynchronous DNS requests? I use a library called Series. I would really like to write my own asynchronous DNS thing, but DNS is extremely complicated, and I'm fearful of doing it. But yes, I use Series, which is a nice little C library, which is what curl uses. It's by the same author. It's fairly minimal and good. It does it on the event loop, right? It doesn't do it in a thread pool.
So how do you deal with specialized systems like Apple's resolver doing .local?
Sorry. Oh, right. Yeah. So I don't.
Okay.
I have a binding to get address info, which executes in the thread pool. So if you want to, so what I do actually is I branch on .local and I go to the system call so that you can go to the name services for non-internet domain names. DNS is so fucked. It's such like, I mean, my God, it's just a hash table. I mean, why is it so complicated? It's very hard, and it's very annoying. But luckily, there's C areas. Yes?
What's the largest or most impressive deployment of Node.js that you're aware of?
So there's a website called Plurk, which is Twitter for Japan, I think. I'm not sure, which has reported hundreds of thousands of users on Node instances. Yahoo Mail is, I'm not sure what their deployment status is, but they are working on it heavily. I think, yeah, that's about it. Yes?
In some of the examples, the write calls appeared synchronous. Is the like this like when you write to
I can't hear you so well. Can you come up here?
this will be the last question.
Okay, this will be the last question.
So, in some of the examples, the write calls appear to be written in synchronous style.
Oh, right. So I write to the socket, right? And it may be that the kernel send buffer is full. Like what's going to happen, right? That's your question, right? So it's very difficult to deal with that situation in C land, and basically everybody buffers it internally when they can't do it. I mean, you want to write that data out. What you do want to be notified is that the kernel send buffer is full, and that like you should really stop writing data right now. You should back off. It is suggested that you back off. The return value to write is true or false. True being, okay, we could flush it to the send buffer. False being, we could not flush it to the send buffer. We buffered it in user space, and when that file descriptor becomes writable, we will flush it out to the send buffer. But you should really stop writing to me right now, or you're going to fill up memory. So that is completely non-blocking, and it is possible to throttle TCP sockets. If you're uploading a file to somebody, you can't just dump that into memory, right? If it's a very large file, you need to do it, pull it off the disk, put it into the socket, pull it off the disk, put it in the socket. And so there's notifications for that. But for the normal users who just approach this for the first time, they don't want to deal with, oh my God, okay, now the send buffer's full. I have to write this whole crazy, get notified when it's not full and do it. So Node buffers it internally by default. Okay, so thank you, and please come and ask me questions later. I'm happy to answer them.